Okay, welcome everybody to this new seminar of the Advanced Computing and Machine Learning thematic area. Thank you for coming today. I'm very happy to have Esteban Ferrer joining to give us a seminar about his latest research. I'm going to go through his biography first. So Esteban Ferrer is a professor in applied mathematics in the School of Aeronautics at UPM in Spain, in Madrid. He obtained his PhD by the University of Oxford in the UK and has 20 years of industrial and academic experience in developing numerical techniques for fluid problems. He works actively with industry and coordinates the ITM project Asimia. He has written 81 journal and conference papers, has received more than 1,360 citations, and his main interests include high-order methods for fluid dynamics, turbulence modeling, stability analysis, aeroacoustics, optimization and flow control for aeronautics and wind energy. So thank you very much, Esteban, for coming today. The floor is yours.
Thank you very much, Ricardo, for the invitation. Right, so today I'm thinking of presenting the newest developments that we have in our own in-house solver, which is called Horses 3D. And I will show you a few new ideas that we have implemented. So I would like to thank, of course, my collaborators, particularly Ricardo for inviting me, my collaborators at UPM and some external collaborators, and especially the students who have done most of the work, and also the funding bodies that have helped perform these simulations and this research. So in our group, we develop numerical methods for incompressible, compressible solvers, and I will be talking about this part in particular today. In particular, we focus on discontinuous Galerkin techniques. We also do flow control based on stability sensitivity analysis, but I'm not going to be talking about that today. And we apply all these types of techniques to aeronautical applications, wind and tidal turbines, multi-phase flows, etc. Right, so the outline for the talk today is I'm going to give a brief introduction to high-order methods, and in particular discontinuous Galerkin. And then I'm going to be talking about the multi-physics we have included in our solver, high-order solver, which is called Horses 3D. In particular, we'll be talking about moving meshes, multi-phase, turbulence, aeroacoustics, and then some new developments that we are quite excited about, which are including machine learning to accelerate or to do alternative things with machine learning in the context of CFD. So I'll start with a brief introduction. So high-order methods, in low-order methods, we typically have a mesh made of triangles, and we have either a constant polynomial or a linear polynomial inside each element to capture the solution. In higher methods, we relax this constraint and we can have quadratic polynomials, cubic polynomials to better capture the solution inside each of the elements. That allows us to do two things. One, we can increase the number of triangles, fixing the polynomial to get a better solution. Or alternatively, we can fix the number of triangles and increase the polynomial in each element. And both have different error characteristics. So if we check that for a Poisson equation, for example, and we check the relative error in the y-axis against the degrees of freedom on the x-axis that include both the number of elements and the polynomial, and we run simulations with different polynomial orders and in different meshes, what we observe is that if we fix the polynomial to 2 here in these lines, and we only vary the number of triangles, right? These are the different colors. What we observe is a slow decay of the error. That's what we call edge refinement. It's increasing the number of triangles, fixing the polynomial. However, if we fix a very coarse mesh, this is the red curve here, very coarse mesh, and we increase the polynomial order in each simulation, what we observe is a very rapid decay of the error. What this means is that if we want to achieve a particular level of accuracy, for example, here 10 to the -7, we need fewer degrees of freedom with a high polynomial order on a coarse mesh than using a low polynomial on a fine mesh, where we will need many more degrees of freedom. We're outside the graph, in fact. So in reality, this translates into this kind of behavior. So if we compare a higher order method with polynomial order 5 against a lower order method, a commercial code Fluent, and in a very coarse mesh for the higher order method, quite fine for the finite volume, what we observe is that the structures are soon disappearing from the flow because of numerical errors in the lower order schemes, whilst in the higher order methods we keep them for a very long time. meaning that the errors in the solution are much lower, and in fact we get better solutions for longer term. If we go to turbulent problems, we also observe advantages of higher order method. So in the middle we have a DNS simulation. On the right we have a low order unsteady run simulation with a low order method, and we see that more or less we capture the shape of the detached flow that we have here, but of course we lose all the dynamics, all the small structures inside this detached region. In particular, the Kevin Helmholtz instabilities here are completely lost. However, in higher order methods, on a very coarse mesh, you can see here the triangles which are very coarse on a polynomial order 5. What we see is that we don't capture everything. Of course, the mesh is super coarse and it's a very coarse LES computation, but we do capture much more structures that we were capturing with a low order method. So we have this higher order method pretty well developed. We can do many things these days, and I will show you the newest things that we can do. So today we're focusing on the Horses 3D, which is our in-house method. It is available on request, so if you're interested in using it, just let me know and we will give you the possibility of using it, of course. The idea is to make it efficient, so we're using some hexahedral elements to make things efficient. I will show you a little bit how. The things we have included now in our solver are compressible and incompressible solvers. We have entropy energy conserving schemes for stability. We do local pre-adaption. We can do explicit, implicit in time. We have a variety of turbulence models ranging from runs to LES. And then we have some multiphysics, so we can solve multi-phase flows, immerse boundaries, and some other things. I will show you some of these things in detail. Again, this is the website, and then we are now preparing a paper which includes all the latest developments that are a bit explained. So we can do runs, we can compare with other solvers, finite volume solvers, and we can run aircrafts such as this one. I will show you some details later. What's interesting, perhaps, is that because we have this high order possibility of using high polynomial orders, when we combine MPI with OpenMP, we get very good scaling properties, especially at high order. So we reach almost ideal scale speedups for high polynomial orders. And this is due to the locality of the degrees of freedom inside each other. We have run some more cases with different wings. And what we observe, due to the efficiency of our implementation and also due to the parallelization strategy, what we see is that when we run different wings, so this is one wing, this is a different wing with a different edge mesh, this is a different one, and the points correspond to polynomial orders, what we see is a linear increase in the polynomial, in the cost with when we increase the polynomial order. So this is P2, P3, P4, P5. So remember that the decrease in error is exponential, but the cost increase, it's only linear. So that tells us that it's very advantageous to use higher order polynomials with our solver. So to finalize, this was in fact, we were looking at the acoustics of these wings, the ones that I just showed you. And we are seeing that we can, if we monitor the some pressure levels at some particular points, for example, like this one, what we get is a polynomial, an exponential decrease of the error. So we get P convergence as we get to higher polynomial orders, right? Whilst the cost is still only linear. Right, so this is about a little bit about the solver. Now I'm going to show you some specifics of the multiphysics. Right, so in the past, we have worked a lot with sliding meshes. So sliding meshes allows you to rotate some part of the domain, for example, whilst the other part is steady. We get hanging nodes, and it's a method that it can be easily handled with discontinuous Galerkin methods because we have discontinuities in between the interfaces. However, it's a bit costly as a method, right? Because you have to interpolate, you have to compute interfaces. Well, it's not the cheapest. So these days we are focusing a bit more on immerse boundaries, which allows us to do similar stuff. So immerse boundaries is a mesh-free method. Mesh-free meaning we only need a Cartesian mesh. So typically we use Cartesian meshes that don't have to be body fitted, so you don't need to mesh much. and then we do some local peer refinement in some particular regions of the domain. What we do, the method works like we define an interface, we define a CAD model, right, with an STL CAD, and this is seen by the solver, and the solver adds some source terms that represent the body inside the mesh. So we don't need to represent the body explicitly in the mesh. It's just an STL file that we import, and then the solver will include some forcing in these parts. By doing so, we can easily, without needing to mesh almost anything, we can do complex geometries, and we can do moving geometries quite easily. Right, so remember, there's no meshing involved, or not costly meshing involved, and this is the main advantage of this method. Right, so with this setup, what we can do is run cases of moving NACAs, for example. Here you have a couple of examples. You have the specifics in these two papers at the bottom, if you want to see the proper results. We can do pinching and plunging as well, and we see that we get very good agreement with the reference values. So one of the things that are typically criticized for this immersed boundary method, it's the accuracy, it's typically lost. So why use higher order method if you're going to lose the accuracy near the water and things like that? Right, so for this, we have checked that increasing the polynomial order, we do get exponential convergence. We get much better results, much more accurate results when we increase the polynomial order. Right, so we are not losing the nice properties of higher order methods when we use these immersed boundary methods. Right, so I'll show you one last case. So this is the immersed boundary method for a wind turbine, which is going to be rotating, well, the rotor is going to be rotating, right? So to do the setup, we only need the CAD file, an STL file, right? We need a simple Cartesian grid that can be homogeneous or can be a bit refined in certain places if you want, but you don't need body fitted, so it's only an easy to make mesh, right? And the solver is gonna add some points where this is already in the mesh, right? So it's gonna select some points where it has to penalize, where it has to add some source terms to mimic the effect of the wind turbine. So if we have a look, what we see is this kind of mesh. So here you can see the whole mesh. We have refined a little bit in this region, but it's kind of Cartesian, so it's meshed all throughout the turbine, right? But we will get some flow field inside. In this particular case, we have increased the polynomial order to P3 here, and we have left it to P2 outside to get better capture the rotor and the wake. But this again is very easy to do. And then if I overlap on top of the solution the STL file, I can see the effect of the blades are, in fact, so the STL is really not there. So it's just this one is the flow field, really, right? But if I overlap it, we can see really the effect of the tip vortices, and everything is well captured, right? So this finally you get this solution when we can overlap the STL, but in fact it's not necessary. It's not really there. So, okay, I hope that. Right, so now we have a variety of ways in our solver to compute rotating turbines, fans, and propellants, right? In particular, we have in the past, we use actuator disk. We have now a couple of different implementations for actuator lines, which do not resolve the blades, just add forces for the blades, but you can get the effect of rotation as well.
Sí, espera, un momento. Ahora.
Miguel, muteate, porfa. Miguel, muteate.
¿Me escuchas, Alex?
Miguel, por favor, muteate.
Sí, ahora mejor.
Please, if everybody can mute themselves.
Vale,
right, so the actuator line, we have also the immersed boundaries. We have just seen that, and we have in the past used sliding meshes. In the near future, we would like to compare all of these and try to correct the low cost models, so those ones here, with the information we get from high costly models. But that's the future. Right, regarding multi-phase, what we do is we use phase field models. So phase field models capture a diffuse interface, such as this one, for the water and air, for example, through the Canhillier equation. So we solve Navier-Stokes plus an additional Canhillier equation to get the effect of the multi-phase field. With this, we can run different test cases, typical test cases. We have a few papers on that. And one of the latest things we have done is we have allowed for peer refinement across the interface. So we increase the polynomial order only at the interface, and that allows us to have much quicker solutions of 50% or less. One of the key points in our formulation for multiphase is that we use entropy stable methods. So these are much more robust than classic methods. And I'll tell you only the main idea of this. So the continuous equations, we typically solve the Navier-Stokes equation. We do exactly the same. We solve the Navier-Stokes equation. But if you think of the continuous equations, this also, it's easy to check that they conserve kinetic energy or entropy, right? This is in the continuous setting. Now, typically, when you discretize these equations, you don't check if these new equations satisfy kinetic energy conservation or entropy conservation. So what we do in the entropy energy stable setup is we check that the discrete version of the Navier-Stokes equation also fulfill these additional equations, like energy equation. Since we have an equation for energy, a conservation equation for energy, we ensure that the energy cannot blow up, it cannot increase infinitely because it's conserved. Right, so there's a few techniques to do so in higher order methods. I'm not boring you with details, but we know how to do it, and we have developed these things for multiphase. Right, so if we see what we observe typically is that if the interface is very smooth, so everything is very well resolved, such as in this case, both the standard DG and the energy conserving DG, they both converge quite nicely. Now, if we get under-resolved interfaces, so we start getting oscillations and we start getting perhaps not enough resolution, DNS type resolution at the interface, what we see is that typically the non-energy conserving blows up eventually, whilst the energy conserving keeps going and gives a good solution. And we can see that for different regimes with different interfaces. But this is the typical trend. Right, so that was for multiphase. By the way, we use these energy stable schemes also for turbulence because we have this problem of under resolution and we get more robust methods. Right, let us talk a little bit about turbulence. So in turbulence, we have now developed higher order runs. So that's Spalatalman's negative. And this is the slide I showed you at the beginning where we're comparing with a well-known Numeka CFD code. That's made by Numeka company, right? And we see similar flow fields. And when we compare the convergence, again, if we use higher order methods, we see much quicker convergence towards the right values than when we use lower order methods. So this is Numeka solver finite volume method. Another example is this hemisphere cylinder. Sorry, I forgot the Reynolds is here. So this is again a RANS computation. And again, when we compare, this is a workshop by NASA. We can see also the nice convergence of our method when we get to high polynomial orders with fewer degrees of freedom, always using fewer degrees of freedom than finite volume methods. Okay, I'm not going to give a talk at all about how we converge to steady state for RANs, but that's a whole other lecture. I just mentioned that we have quite efficient methods to converge to steady state, right? So we basically combine fast multigrid with semi-implicit smoothers, and we are getting quite convergence in quite reasonable times. Okay. The other way to deal with turbulence is use implicit LES, large eddy simulation. So to do LES, you can do implicit LES, you can do explicit LES. So I'll just show a little bit on the implicit LES side. So to do implicit LES, what you want is the numerical errors to act as a subgrid model for the large eddy simulation, right? To have an implicit method that works well, you need, we think, to characterize the numerical errors, and we typically do that through the von Neumann type analysis, where we know, we can see at which wave numbers the errors start acting. Second, the errors should have a predominantly dissipative character, and hence can diffuse the non-resolved features in the subgrid, and they should act at the correct wave number. So typically at quite medium to high wave numbers. So for example, this would be, I have here a typical Kolmogorov cascade, energy against wave number, and what we see is that a good numerical behavior for implicit LES would be something like this. It follows well everything when it's well captured, and then suddenly drops at the cutting wavelengths. And a bad behavior for implicit LES would be something that it's adding dissipation everywhere and maybe not enough, and there's some accumulation of energy at the wavelengths of the cutoff. Right, so there's different ways of adding dissipation in numerical schemes. You can look at the Riemann solvers, in particular in DG, you have Riemann solvers, you can add some dissipation there. You can add dissipation in the viscous terms, or even add artificial dissipation that would be almost explicit LES. So we've tried different things. I will show you just some solutions where we have compared compressible solvers, incompressible solvers with different implicit mechanisms to add subgrid, and we get reasonable results for CL, leaf, and drag coefficients. Here you have the polar leaf against drag for I think that's the NACA 00 trans for different angles of attack. What we're doing now in collaboration with Oriol Lemhout from BSc is we are going, so the big picture, the CL and the drag are okay, the lift and drag are okay, but now we're looking at the small, we're zooming in and trying to see what are the differences, in fact, of using implicit and explicit methods. We have everything in our solver, so we are running some fine computations and see how the boundary layer changes, where the separation occurs, and all these kind of things for different flows. Right, regarding aeroacoustics, I've shown you this picture before. So this was the convergence of the sound pressure levels for some particular measuring point here. And what we have done also is check the effect of tripping. So this is triggering the boundary layer to become turbulent at some particular point. For this, we have used this paper of Philip Slater, and we have implemented it for our airfoils. And what we observe is that there's a huge change in the directivity of the acoustics when we measure it in these particular locations, right? So what we see is that without triggering, we get typical cardioid shapes for the directivity, whilst for triggered transition, we get a much more rounded thing. So this is ongoing work, and this all has to do with how you set up the parameters, the amplitudes of these perturbations that are going to trigger the transition. By the way, here we are also comparing Fowell and Hawkins with direct computations, and there are some small differences that we're trying to explain as well. Just one slide on ongoing work as well on shocks. So we are also working on capturing shocks in our solver. We have different methods of doing so, but this could be another complete talk. Right, I'm coming towards the second part, the last part, where I'm gonna show you some new avenues, we think, in how we can accelerate CFD, right? And this involves some machine learning, adaptation, or things like that. Right, so one of the ideas that we're very excited about is to use machine learning to accelerate CFD. So we're not trying to get rid of the CFD at all, but we use machine learning to go hand by hand with the CFD. So the main idea is if we have a high order method, so this is a high order polynomial, we need a very small time step because of CFL restrictions. Whilst if we use a low polynomial order, a coarse mesh resolution, we can use much larger time steps. And so the idea is, could we perhaps try to increase, so can we run a low order method with the accuracy of a high order method? That's perhaps the question. And the answer is, I think we have managed to do it. What we do is we will run a low order method. So this is this curve, and we can correct at some point, adding some source term to correct the lower order method to retrieve the accuracy of higher order methods. If we have this tool at hand, what we can do is increase the time step to the low order limits and bypass the high order CFL restrictions. That's the main idea. So how do we do that? Of course, it's a simplified explanation, but the idea is we have a low order evolution. This is just explicit Euler for simplification. Q will be our Navier-Stokes operator. And this will be advancing the low order solution. So this, we will not gain anything. The higher the solution, we can think of the filter higher order solution, and this will follow the same time advancing technique. Now, what we propose is to use a low order. So this is exactly the same as the first one. It's a low order time evolution, but corrected such that this correction term will make this guy become like the high order filter solution, right? So we need to find this S that corrects us the low order solution to retrieve the high order accuracy. How can we do that? Well, the answer is machine learning. These days, most of the answers are machine learning, and we don't know how to do things. So what we do is, we know S is a function of the solution in previous times, and we can train a neural network with U as an input, and such that we get the S's, the functions as an output. If we do so, we can correct the low order solution. We retrieve the higher order solution. So we have tried that for 1D Burger's equation. So we have a paper on 1D where we explain all the techniques, all the ideas, and now we're working on the 3D, of course. So in 1D, what we observe is that if we go from P5 to P0, so this is the higher solution to the lower solution, we correct the lower the solution, we can advance the lower the solution by a factor of 100 in terms of time step, which gives us a speed of almost 60, right? And then when we compare and we reconstruct the solution after advancing it, we see that the high order and the low order are exactly the same. Of course, we have done that also for more complex flows. This is the work in progress, but we have some solutions for Taylor-Green. So this is a turbulent flow at Reynolds 1600. And what we see, for those who don't know the Taylor-Green, this is an evolution of some vertical structures, and then you get turbulence, and then you get isotropic decay in turbulence. This is with time. So what we do here is we're gonna use polynomial order 8 and polynomial order 3. That gives us a speed of factor, quite conservative, I would say, of 3. We could even increase that. Right, and what we observe is that we can go 12 times faster than if we were using the higher order method, with almost the same accuracy. So here you have the error on this axis. You have time here. So we will start training at 7. We will train for a while. We will train for this part, and then we don't train anymore. And we use the forcing that we have trained in this previous time. And what we see is that the error when we have the forcing, this is with forcing, this is without the forcing, and this is the change between low order. So the error between when we compare low order against high order solutions, right? So this is the error is quite big because we have quite difference between low order and high order solution. When we add the forcing, this S forcing that corrects, we get a much more accurate solution for a very long time, right? All this is time that we are gaining in our low order solution, having a quite accurate solution. Of course, eventually the errors, so the neural network that we train is not working anymore. So up to this point, here we have to train again for a while and leave it and train and leave it, etc. But we observe quite interesting saving times. But together with Ricardo, we also, and Stefano from KTH, we are also working on combining pins with the ideas that I just mentioned. So this is work in progress. Hopefully soon we'll have some results. Right, in the past, we have worked with mesh adaptation. So mesh adaptation is refining the polynomial order in particular areas of the domain. We have quite a few papers on truncation error estimates. I'll just explain the idea because it's very easy. So if this is our Navier-Stokes equation, I'll show you for steady state only, right? See, in the steady state case, this term is 0, right? And the truncation error can be defined as this. right? Switch on list. So this is the Navier-Stokes operator with some particular discretization evaluated at the exact velocity, right? Exact solution. So we don't have the exact solution, but what we can do is estimate the exact solution with a much finer polynomial, with a much finer resolution, right? So, and this will give us these truncation errors where we estimate the exact solution at P, and we have the R, the Navier-Stokes operator, evaluated at a coarser resolution N. Right, if we do that, what we have to do is we run one simulation, this in particular, and then this is the P step. We solved for this, for P, and then with the solution we obtain for P, we only have to evaluate all these operators with this solution. This is not solving the Navier-Stokes equation, just taking the solution and inputting in the coarser levels, right? So it's not solving more problems. So what we see is that truncation error shows exponential convergence, similar to the errors that I showed you at the very beginning. And hence, because we know it's an exponential behavior, we can throw a line, we can do an interpolation and extrapolate towards the values that we want for the error. So we can extrapolate and see that we need in this particular element, we do that element per element, we can see that here we need a polynomial of the 10 in this particular case to get the error that we want. We can do that in multiple directions. So we have that in isotropic, anisotropic manner. So we have in X and Y directions, etc. And this allows us to save a lot of degrees of freedom. So we can see homogeneous refinement here against this local peer refinement technique in different directions. Just very quickly, no, I will jump that. Right, so I'm coming towards the last application. So this, what I was talking about, it was typical mesh adaptation, the classic mesh adaptation technique. So now we are proposing a different idea, also linked to machine learning. Our idea now is to use machine learning to detect flow regions. So if you think of the typical sensors to see regions in the flow domain, for example, the eddy viscosity sensor, you need to select a threshold, right? So you are to plot the vorticity level, you need the levels of vorticity. No? So you need to give a value, and that will give you isocontours of this particular value. So this happens with almost all the sensors. So the eddy viscosity, for example, will allow you to detect these regions of high eddy viscosity in the wake of this circular cylinder at Reynolds 3900. But if you change the values of the threshold, the structures that you get, so the regions that you get, change quite a bit. Right, so it's very sensitive. All the thresholds that we know, they're very sensitive to the values selected, and often they cannot detect mixed regions. For example, here we have a laminar region within this turbulent region, this blue thing here, and it's not incorporated in the eddy viscosity because that's only for turbulent part. So what we were proposing is to use some clustering technique based on Gaussian mixture models, and these can automatically detect, without any need for any threshold, particular regions. So the regions that we're going to detect are going to depend on the feature space, on the variables that we throw into our clustering model. So we have, we think, a robust feature space model for a variety of Reynolds numbers, where we include viscous dissipation, vorticity, etc., as variables, and we are able to detect all these regions in the wake of the cylinder and the boundary layer. So we capture the boundary layer and the wake, including these laminar regions and these turbulent regions. To check that we're doing things right, what we can do is we can compare two of these variables that we have. So this is dissipation and rotation for the values we have inside the red region, inside the boundary layer and wake. And we see that we get values that are between 0 and 1, where we have non-dimensionalized that by the maximum value in the whole domain. So we're getting most of all the values that have dissipation and rotation are in the region that we have obtained. If we do the same for the outer flow, we see that the values are almost negligible, meaning that there's almost no value, no points in this outer flow that have a big value of rotation and dissipation. In addition, this clustering tells us something about the features that are included in the flow. So we can see vortex sheet structures, vortex tube structures, depending on how these correlations behave. So why do we want to use that? So we're thinking of using this for p-adaptation, where we will include the polynomial order, we will increase the polynomial order in the regions that have high turbulence and high viscosity, so both laminar, boundary layer, wakes, etc., and use a low polynomial outside. So this is soon to come. I will finish with this and some very brief conclusions. I think we have a solver that, again, is available on request and shows exponential decrease of the error, but linear increase in cost only. We have quite a few multi-physics included, and we are working on combining some new ideas with mesh adaptation, but also machine learning, etc. So with this, I'll finish. Thank you very much.
Thank you very much, Esteban. Very nice presentation. Any questions? I would like to ask you, Esteban, I think it was nice the part that you showed where you have the forcing with machine learning and how it, well, you have very good results for a while, that it increases with time. What type of architecture are you using for that section?
Right, so it's a typical neural network. The only slightly the only thing, I mean, of course, I think with machine learning you have to try, right? So we have tried many architectures. So it's a classic neural network with many layers. It's a deep neural network. What we have tried to do is increase the number of the width of the layers eventually to try to, if this helped, and it did help a little bit to increase the complexity.
SN, so this term, which is a force for each point in space, right?
That's, yes, that's correct.
Because the architecture that you're using, which is a fully connected network, an MLP, maybe using some more advanced like versions, no, that you can exploit convolutions, or you can exploit the spatial information in the data. Maybe that could give better results. And the other thing that could be interesting would be, I mean, of course, it's natural that the error is increasing with time, but there might be ways to embed temporal predictions as well, because here, of course, you don't really exploit the temporal correlations or spatial correlations in the data, but maybe with certain architectures like combining recurrency in time and then spatial, then maybe one can get better results.
In fact, we have done that in a brute force way. So we have included the dependency of the current time and previous times. Am I sharing this? You're seeing my screen, right? So
yeah, we can see your screen.
Okay,
yeah.
okay. So we have tried to include the information of the current time and previous times, up to 5 previous times, for example, which is giving you a sense of the history of the evolution, right? So it's kind of a recurring neural network, more or less, less expensive probably, and we do see a little bit of the advantage in doing that.
I'm sorry, when you include the previous time steps, do you do it in the input of the MLP?
Yeah.
Because then the network can learn a bit of the history, but the network doesn't really know exactly how the steps are ordered in time.
That's correct. That's correct.
Well, with a recurrent, you would know that. But something that could be interesting, and we could discuss if you want, it would be to use transformers for this, because we have been using transformers for inflow generators in turbulent boundary layers, and they work even better than recurrent networks. They're very good at temporal predictions in turbulence. And for the spatial stuff, we could think of starting with a CNN maybe, but even GANs or something like that, so that you can more effectively use the spatial information that you have in your field.
Yeah, that's right. I mean, the convolutional neural network was mainly because of an implementation issue. So the way we were doing it wasn't easy to couple with convolutional, but of course that was the.
But to be honest, even with this architecture, which is reasonably simple, it's quite impressive, the improvement that you get. I mean, it's quite nice.
We think so too. I mean, there's a few things we haven't mentioned, right? So got devil is in the detail. No, in here we have tried different Reynolds number for the Taylor Green, and you get different advantages depending on how smooth is your solution. So what we are developing in the new paper, it's an estimation of the smoothness of the solution, such that we know how much we can do in these jumps, right? If we need an LES model or not, we can do a DNS. That depends on the resolution, or in the coarse level, and also in the fine level, in the coarse and the fine level, right? And that all the smoothness of the solution is what tells you also how much you can gain in these things.
I'm also thinking that for different Reynolds numbers, one can actually, I mean, of course, you have transfer learning, but there are other ways in which you could have a network that is able to extend to different Reynolds numbers that have not been seen during the training, which could also be quite promising. But yeah. I think this is a very nice direction. This is very cool. Yeah.
Yeah, we're quite excited about this. So, yeah, but there's lots of things to try, as you mentioned. So.
Oh, very, very nice. Thank you. More questions? Not, then let's thank the speaker again. Thank you very much, Esteban.
Thank you very much.
Esteban is going to be here today, the whole day. So if you're interested in discussing, I mean, just come by his office. I also copied him in the email of the thematic area. So you have his email information if you want to directly contact him. Yeah, and anyway, I mean, he's available, and I can also help you arrange a meeting if you want. Other than that, thank you very much, and have everybody a good day.
Thank you very much.
Bye-bye.
Bye.
Bye. Thank you.